There we go. Ah, excellent, excellent. My name's Tim Massey. I'm the CEO of SoftIron. We're a young company, and we're just making the rounds at these kinds of conferences, and I'm delighted to be with you here today in Barcelona. At SoftIron, we make a portfolio of fully supported Ceph appliances, and we are all in on Ceph. We're so confident that Ceph can become the de facto standard of storage that we're willing to bet our entire company on it. Ceph will win the open source projects like other open source projects have. And that is not by doing any one particular thing extremely well, but by being versatile and having the ability to scale. Ceph is a Swiss Army knife. It's already reached critical mass, and the adoption will snowball from here. So if you want to see what adoption looks like, look around the room today. You can see that there's many organizations here that have done massive Ceph deployments, and it's an honor to be involved. No other storage open source project is innovating as quickly as Ceph is. The more it's deployed, the faster it grows. After all, open source software gives organizations the freedom to choose their vendors, and while at the same time preserving a common user model and protocol. I know you guys already know this, and we're proud to be a part of it. In this way, the end user can maintain control of their software base and can never be held over a barrel by being locked into a single vendor, not even SoftIron. We know that building your own Ceph estate does work, and many of you here have already done it. But it can also be hard to bring up, it can be hard to get right, and it can be hard to maintain over time. SoftIron, and to the greater extent the Ceph community as a whole, is on a quest to build the very best Ceph storages we can. And as you know, Ceph can run on anything. It can run on a generic server or a Raspberry Pi or even a toaster. But if we ran Ceph on a toaster or a Raspberry Pi or a generic server, it wouldn't live up to its full potential. We can do better than that. So if we started with a black box and we said, what's the very best system we could build? What would that system look like? Well, it would have zero latency. It would have an infinite capacity. It would use no power. It would be simple to use, and it would be essentially free. That would be the holy grail of storage. But unfortunately, the real world gets in the way. But still, we should be able to ask the question, how good can it be? How good could it be? That's the way we think about it at SoftIron. We are obsessed with every part of the system. We're obsessed with the OS and with the drivers, right down to the boot code and all aspects of the hardware. And to that end, we take great pain in removing bottlenecks from the system as a whole and selecting just the right processor for the job. We do our best to make it easy to use and to add hardware acceleration when it makes sense. Now, I know that many of you here consider your prowess on the command line as a badge of honor. We have found that there are many organizations that just want to buy great storage, and they want it fully supported. So if we can get to this last frontier, if we can get to a place where Ceph is performant, where it's low power, it's easy to use, and it preserves the customer's freedom to choose, we can accelerate the mass adoption of Ceph. And that will be good for us all. So today, we are announcing, and you may have seen this, that we have included hardware acceleration in our storage products. And to tell you more about that, I'd like to invite Phil Straw up to the stage and give us his view.
Thanks, Tim.
Thank you.
Hey, it's great to be here. You know, at SoftIron, we focus on Ceph, and we do that every day. And so over time, that's become many years. And so when we get a few days to do something like Cephlicon, that's really iconic to us. So hi there, Ceph brothers and sisters. So we focus on a systems approach, as Tim said, for both the Ceph experience and Ceph productization. Tim mentioned results, things like power, performance, reliability, quality, ease of use, all that good stuff. And so on this grail quest of trying to find the best Ceph system, we often take a path less traveled. Often it's radical, at least at the start, but it's in the search of results, and it's an interesting story. And that's really what I want to talk to you about today. So it's easy to talk about results. Tim's obsessed with it. It's something of a corporate obsession for us. But as a technologist, what's interesting to me is how. And recently we got a lot of press.
No, don't tell me.
Yeah, keep it real, Tim. Have some fun. So, you know, I'm known for my subtlety, and I happen to mention that in order to make a really, really awesome Ceph storage product, maybe you'd make a rather weaker computer, and somehow that happened. I don't know how that happened. But said another way, focusing just on compute alone is by far and away not the only way that you can get performance in multiple vectors for Ceph. And often, I'll give you an example of this. So often as silicon is productized and it gets faster and faster, you end up with things like I/O paths versus compute paths become a compromise. You get things like peripheral chaining, I/O bridging, wait states, various different things with buffers, and also lots of excess heat. At the point that you don't need that compute, it's just heat, and that's orthogonal and toxic to a great storage product of any kind. And so, that's kind of one factor that we were talking about in this systems approach that led to this press that got into Slashdot and register and everything else. So in our journey, there's been a lot of technological leverage. And in this path less traveled, I would say that there's a lot less headache medicine in the cabinet than when we started. Basically, what we're probably best known for is leveraging ARM64 to effect to make a really great Ceph product. Recently, x86 also, and that's an interesting talk all on its own, but probably beyond the scope today, there's a place for x86 and a place for ARM64. They can make music together, and they have different roles in different places at different points in performance. We've done things like create caddy technology that holds drives and allows you to identify them and monitor them in the real world in a really easy way, allowing hardware to know about Ceph and Ceph to know about hardware. And most recently, we've taken multiprocessor technology in a way that's not dual socket or multi-node in a really unique way and overlaid it with network matrix technology that allows us to do things in a product category which is unusual and unique, which is very, very high density, very, very high performance, and very, very low power in a 1U box. And when you find customers that really care about that category, they tend to really care. So we're making people happy, right, Tim?
Indeed.
So a next step for us, we're here announcing that we're going to do Ceph acceleration in silicon. And this is kind of a big step for us. So going to 100,000 feet, what works in hardware generally is something that happens in parallel. And by definition, in a CPU, things happen serially. Instructions ALU gets clocked through, and it does that really, really, really well. But there's a place for both. And so if you look at Ceph, usually there are a lot of drives. They're all connected to OSDs in a computer, and then you have multiple computers in a cluster. It's parallel in many ways in many tiers, and so there should be opportunity here, right? So where can you not make things parallel? Well, computing science 101, just to review, is sequence selection and dependent repetition. And so what happens is when you find something that's exhaustively done in a CPU in software that is actually independent, that's a possibility for parallelism. And so acceleration, at least in theory. And so when we looked at Ceph at the lowest levels, what we found is that there are opportunities galore. There are an embarrassment of riches far from the hardware, close to the hardware, and everywhere else. And so the first thing that we picked is really erasure encoding. And erasure encoding means a lot of things to a lot of people, but it basically usually boils down to a result that everyone agrees on, which is brilliant economics. Data protection can be achieved a number of ways. One is triple replication. That's fairly easy to understand. But also erasure encoding is an alternative, and you can achieve similar levels of data protection with less footprint. So by that, I mean less bytes, less data used in Ceph to store the data you care about after data protection's occurred. So that means less drives, less computers, just less, and so that means less money, and there's the economics, right? So pretty simple. In this talk, I'm going to talk about erasure encoding, which can have different options and different geometries. I'm going to pick 6+2 for this talk, just so you know what I'm using. I'll use it consistently. If you don't know what that means, you're truly blessed. I wouldn't go and research it. You'll just need that headache medicine. So it's not really important to talk.
When we started the company, he still had hair.
I miss my dreadlocks, you know. I figure the way it is, I was born bald, and so I'm actually getting younger. So, see what I did there, Tim. So, acceleration for us, accelerating erasure encoding, is really about opening up the aperture for erasure encoding, making it relevant to places that may or may not have been relevant before. So the headline is really about storage space and storage efficiency. And if you pick this geometry and you compare it to triple replication, you would get an amplification of data of 3 times, but with this erasure encoding of 6 + 2, you would end up with 1 1/3 bytes of amplification. So you don't have to be a math professor to understand that it's less than 50% of the space and cost, or 2 times for a set euro. And so that boils down unfettered and undiluted directly to economics. And acceleration of erasure encoding really is about creation mathematics. So anytime you have a read error, in particular write or hardware recovery, this is a place that hardware can actually do real acceleration. So not only can you do write and recovery and accelerate that sometimes in an order of magnitude, but you can also, as a second order effect, alleviate the burden on the processor. And this is really important. So one of the things that this does is allow the processor to concentrate on front-side delivery, making clients happy, being the best possible Ceph product and Ceph experience that you can have, leaving the processor just to do some housekeeping and some DMA, which is hardware handoff. So it leaves the processor pretty much undiluted, which in the real world is pretty much as close as you can get to a free lunch. So this allows allows erasure encoding to be more applicable in more places in different workloads, and that allows those economics to trickle down into Ceph and be applicable, to a wider audience in more places, doing more things, and that's just good for Ceph. And in this talk, I promised a commentary on a journey, perhaps, and it wouldn't be complete without talking about what we learned and what the milestones were and some of the events that happened in this productization. So we had a team of people work on this for well over a year, including hardware guys, software guys, systems and optimization guys, obviously silicon guys. And what we found is that we made a first instance proof, something that works, and we put it in hardware. And the net is that, as you would say here, no bueno. So, basically it was a non-result. It would work, it was an instance proof, it was technically correct, but it didn't matter because the way we implemented it, would use standard hardware handoff, standard kits for doing this. We tried to pull the easy lever, and the results really weren't in. It was just the same as doing it in software. There was no net benefit of handing off that way. And so you can forgive us for pulling the easy lever, but we then looked at what we normally do every day, which is a systems approach. And in doing that, we looked at software and hardware. We looked underneath the level of source code, underneath RTL that creates the silicon. And we did a bunch of things to match hardware to drivers to the operating system, and match Ceph to make Ceph feed hardware well and hardware to feed software well. And what I mean by that is very, very, very performant. So taking out all of the extra abstractions and fat and trying to match those two things exactly. And so said in a human way, and I'm not known for this, is we created a recipe to make an erasure encoding meal that's very tasty for hardware. And I'm working for a living here. It's not what I do naturally. So some things have to happen in software, and some things have to happen in hardware. And we talked about parallel versus serial, hardware, software. But in the real world, that black and white becomes gray very quickly. And one example is that hardware is a finite resource. You can think of software in many ways over time as an infinite resource. But if you create a piece of silicon for parallelism, you have a certain amount of real estate you can use. And so there are only so many things you can do in parallel at one time. So immediately in runtime, you have a resource management issue. It's now not just a gray day, it's raining outside. You have a backwards and forwards latency of sending things to acceleration and getting it back. And so now in both design time and runtime, you have a decision about not only resource availability, but what's actually going to have a net acceleration and what's not. And some things do and some things don't, as it turns out. So we've gone from a 100,000-foot view of parallel serial to maybe a 50,000-foot view of it's really complicated. And we got through this, we pushed through this systems approach, and the kind of results are in. We're here, proof's in the pudding, and we've kind of arrived. But what I can tell you is that arrival for us here is just a pit stop. When we made our laundry list of things that you could parallelize in Ceph to make a better Ceph product, what we learned is what we're going to do next is probably more impactful than just erasure encoding. So that's super interesting. It's super exciting. I'll leave you with that cliffhanger because I think we're at 15 past the hour. So I'm on the SotfIron booth. It's booth 102. Jason? 102. So if you want to know all the nerdy details that go beyond kind of, just an introductory talk, I'll be there all day. My name's Phil. I'm friendly. I'm house trained. I'm on booth 102.
Thank you very much.
Thanks.
Thanks, everybody.